Welcome to The Explainer. Today, we're embarking on a pretty incredible microscopic journey, right down into the hidden spaces between atoms. If you're the kind of focused learner who likes getting straight to the core of how the universe works, you are in the right place. We're going to start super small, looking at isolated single atoms. And by the end of this explainer, you'll know exactly how invisible fighting forces dictate the complex 3D shapes of, well, absolutely everything around us. Okay, let's dive into this. Have you ever actually stopped to wonder what determines the physical, architectural structure of a chemical compound? Like, why doesn't a molecule just collapse into some random, messy blob? Well, the answer lies in an invisible force. There is literally a constant, hidden competition happening millions of times a second inside the chemical bonds of every substance in existence. So, to make sense of all this without getting tangled up, we're going to break it down systematically. 1. The atomic tug-of-war. 2. Affinity versus electronegativity. 3. Measuring the invisible. 4. Shaping the molecules. And 5. The periodic rule breakers. Let's get right to it. Section 1. The atomic tug-of-war. All right, let's shift our focus to the microscopic battlefield, where atoms are actually competing over shared resources. We're not talking about atoms just floating around alone here. We're talking about atoms locked together, interacting and vying for control. And that brings us to electronegativity, which is defined as the tendency of an atom to draw electrons to itself in a chemical bond. This whole concept was first proposed by the brilliant Linus Pauling back in 1932. He was basically trying to figure out a really strange puzzle. Why is a covalent bond between two different atoms almost always stronger than the average strength of bonds between identical atoms? Well, he realized there was this additional stabilization kicking in because one atom was pulling the shared electrons just a little bit closer to itself, creating a polar bond. So electronegativity isn't some static property of a lonely atom, it's completely dynamic. It only exists when atoms are actually bonded together. I really want to anchor that idea with this simple, but honestly super powerful quote from our source material: the ability of an atom and a molecule to attract electrons to itself. The absolutely crucial phrase there is "in a molecule." I want you to picture this as an atomic tug-of-war. The rope, that's your shared pair of electrons. The atoms are the competitors. And, some atoms are just much, much stronger polars than others. Section 2. Affinity versus electronegativity. Now, these two concepts get mixed up on exams all the time, but they describe entirely different scenarios. So the crucial point is the context. Electronegativity applies strictly to bonded atoms inside molecules. Electron affinity, on the other hand, applies to isolated, gaseous atoms floating all by themselves. One is this qualitative relative scale of unequal sharing, right? But the other, affinity, is a very strict quantitative measurement of the actual energy released when a lone atom captures a passing electron. And distinguishing between those two gives us this really fascinating paradox. Fluorine is the absolute reigning champion of the tug-of-war. It hoards electrons in a bond like nothing else. But if we look at atoms in total isolation, chlorine is the true electron grabber, releasing the most energy, around negative 349 kilojoules per mole when it captures a free electron. So why does fluorine lose out here? It's simply because it's so small. Its compact 2p orbital creates this intense internal crowding, which makes it surprisingly reluctant to take on a brand new isolated electron from the outside. Section 3. Measuring the invisible. So, if electronegativity is basically just a relative concept describing a macroscopic tug-of-war, how on earth do scientists actually calculate and assign hard numbers to it? Well, the methods really evolved over time. Pauling's original 1932 scale was built on bond dissociation energies, but that had a big limitation. You needed very specific compound data to even calculate it. So other scientists jumped in and developed alternative scales using completely different thermochemical measurements. In 1934, Robert Mulligan used the average of an atom's ionization energy and electron affinity. Fast forward to 1958, Allred and Rochow used electrostatic force and effective nuclear charge. And then in 1989, the Allen scale used the configuration energies of valence shell electrons. But you know what? Despite all these different clever methods, the scientific community largely standardizes around Pauling's original framework. They set the top of the scale at an anchored value of 4.0 for fluorine. It's just a really clean, memorable anchor point for the top of the scale. Francium, way down at the bottom, sits around 0.7. And the gap, the mathematical difference, between the numbers of any two bonded atoms tells you exactly how polar that specific bond is going to be. And this brilliantly illustrates why we can actually trust these numbers. Notice this incredibly tight linear correlation between Mulliken's values, which remember are derived from ionization energy, and Pauling's values, which are derived from bond energies. Even though these guys were measuring totally different thermochemical properties, their data plots into a near-perfect line. It's awesome because it proves that regardless of the math they used, all these scientists were successfully capturing the exact same fundamental behavior of the atoms. Section 4. Shaping the molecules. Let's move on and see how this builds up. How do these invisible pulling forces dictate the actual physical 3D geometries of the molecules we interact with every day? Well, this is governed by valence shell electron pair repulsion theory, or VSEPR for short. Imagine a molecule with a central atom, a few pendant atoms hanging off of it, and a lone pair of non-bonding electrons sitting right on top. If we swap out that central atom for a physically larger one, we trigger a chain reaction. Step 1. The central atom is bigger. Step 2. Because it's bigger, the bond lengths connecting to the pendant atoms physically stretch outwards. Step 3. Because those pendant atoms are now further apart in space, their physical crowding, what chemists call steric interactions, drops. And finally, step 4, because those pendant atoms aren't violently pushing against each other quite as much, that highly repulsive lone pair of electrons on top easily pushes them downward, squeezing the bond angles tighter together. Let's look at the hard data to definitively prove this negative relationship between the central atom size and its resulting bond angle. Here we have a series of molecules where the pendant atoms are always hydrogen, but we're traveling down the periodic table for the central atom. Nitrogen is the smallest, and it creates a bond angle in NH3 of 106.6 degrees. But as we move to larger central atoms, phosphorus, arsenic, and finally antimony, look at what happens. The bond angle steadily drops to 93.2, then 92.1, and all the way down to 91.6 degrees. It's literally a physical squish. The larger the center, the longer the bonds, the less the hydrogens physically repel each other, and the more that lone pair on top squishes them together. But wait, chemistry always throws us a curveball, right? What happens when size and electronegativity go head-to-head as competing factors? Look at NH3 compared to NF3. Fluorine is a larger atom than hydrogen, so based on size alone, the bigger fluorine atoms should clash more, pushing the bond angle wider. But the angle actually shrinks. It goes from 106.6 down to 102.2 degrees. Why? Because electronegativity absolutely overpowers size here. Fluorine is so highly electronegative that it pulls the shared electron density away from the central nitrogen atom. That reduces the electron repulsion right at the center of the molecule, essentially deflating it a bit and allowing those bond angles to close in tighter. Section 5. The periodic rule breakers. Now, general trends across the periodic table are great and all, but what's really interesting about this slide is seeing where those standard rules completely break down. Electronic configuration can totally override these general behaviors. Take noble gases. They basically reject extra electrons like a really bad gift. Their octets are perfectly full, so their electron affinity is near zero, or sometimes even positive. Then you have nitrogen. Even though it's far over to the right of the periodic table, it shows unexpectedly low electron affinity. Why? Because its p subshell is exactly half full, which is a highly stable state that it absolutely refuses to disrupt. And when we look at 3D geometry, specifically molecules with 5 bonds, called trigonal bipyramidal, the less electronegative atoms actually prefer the less crowded equatorial positions around the middle. That happens because their bonding electron pairs stay closer to the central atom, which makes them way more repulsive and requires more physical room than the highly electronegative atoms that pull electrons further away. So, we've journeyed from abstract, invisible forces fighting over a single electron to seeing how those exact forces literally bend and shape the three-dimensional architecture of the molecules themselves. And I think it leaves us with a really provocative final thought to ponder. If just a slight difference in electronegativity can bend a single bond angle from 106 to 102 degrees, how do billions and billions of these micro-level atomic tugs of war scale up to dictate whether the materials around us are liquid, solid, toxic, or even life-saving? That is the incredible, invisible power of chemistry. Thank you for joining me on The Explainer. Keep analyzing, keep questioning.